This is Tech and Politics, and I am Andreas Jungherr. Welcome back to the podcast accompanying the lecture series Digital Media in Politics and Society at the University of Bamberg. In this and the following 3 episodes, we will discuss algorithms and their impact on politics and society. Data are only part of the puzzle. Making sense of data, acting on them, and using them to predict the future asks for algorithms. Algorithms are sets of steps by which to solve predefined tasks. Originally, the term algorithm refers to predefined sets of steps by which people would solve mathematical problems. But today, the term appears predominantly in connection with computing. Algorithms allow computers to perform tasks. They're crucial in the advances of computer-enabled analysis and automation. But the uses of algorithms vary widely. Algorithms can identify patterns in data, surfacing hidden connections between phenomena or actions. Expressing interest in a given brand on social media might be linked to support of a specific party, or being informed about a supposed political crisis might make people donate money to a political party. Potential patterns abound, and algorithms help in identifying them. Similarly, algorithms can also be used to automate actions. Based on rules learned from past data, algorithms can automatically present people with specific options. For example, if in the past people who expressed a liking for a given brand would also go on and support a given party, the algorithm could automatically present them with content from said party without having them first look for it. Or, if in the past specific people reacted to a crisis prompt in an email with a donation, while others reacted to a personal request by the candidate's spouse, the algorithm could automatically decide which recipient to present with which information in an email blast in order to drive donations. Algorithms thus help us understand the world better and interact with it more efficiently. But algorithms are also a source of worry. How can we be sure that patterns identified from data documenting the past should be replicated in the present or future? How can we know what the algorithm learns from data? And how can we be sure that the actions taken by algorithms conform with the goals with which we have designed and deployed them? Studying the use and impact of algorithms in society means being aware of the technical workings, but also their uses in different societal fields. How are algorithms designed? What tasks are they deployed to solve? And how are their uses and outcomes monitored and interrogated, not only by those using them, but also those who are affected by them? The study of algorithms, therefore, has mathematical, computational, and social components. This and the following 3 episodes will provide the listener with an overview of the technical as well as the social components in the study of algorithms. Let's start with the question, what are algorithms? We live in a world shaped by algorithms. In digital communication environments, algorithms decide what information we see, which music or films are suggested to us, or which people we are invited to connect and interact with. Algorithms decide also about whether contributions to digital communication environments are banned and which are allowed. Algorithms are also shaping our world beyond the merely digital part. They also assign people individual risk, be it credit default, fraudulent behavior, abuse, or recidivism. And algorithms act. Algorithms buy and sell stock, and they decide whether a self-driving car should stop or accelerate. Algorithms shape the information we see, options we have, and confront us with actions we have to contend with. No wonder, then, algorithms, their uses, workings, and effects face increasing scrutiny and contention. The term algorithm has become a general catch-all term for the risks and fears associated with the powers computers hold over individual lives and its societal fields. The term has become associated with opaque and incontestable mechanisms that allow governments and companies to control people, or, worse yet, that through runaway technological change have evolved beyond the control of even those who develop or deploy them. But these far-reaching fears and generalizations tend to obscure the actual nature, workings, and effects of the use of algorithms. Instead of inspiring and enabling critical reflection, evaluation, and improvement of algorithms, these accounts risk blanket rejection and a sense of helplessness. To turn widespread interest or concern into something more productive means looking at algorithms more closely and analytically. First, we need to be clear about the term. We have come to associate the term algorithm with computers. But in fact, the term goes back far beyond the age of computation. Algorithm is the Latinized version of Muhammad ibn Musa al-Khwarizmi. Al-Khwarizmi was a 9th century mathematician from a region of Central Asia, south of the Aral Sea, in what today is Uzbekistan and Turkmenistan. He was the author of the earliest known book on algebra. Once the book was translated into Latin in the 12th century, the name of its author became synonymous with the practice of mathematical calculation following routine arithmetic procedures. Accordingly, in mathematics, the term algorithm refers broadly to, and I quote Chabert, any process of systematic calculation that is a process that could be carried out automatically. End quote. This, of course, includes processes that were defined well before there was the term algorithm, such as Euclid's algorithm, that described a routine to identify the greatest common divisor between two numbers, and those that came after, such as Euler's method for solving differential equations. More fundamentally even, we can think of basic math routines performing long division by hand as algorithms. But we can think even more broadly about the term. The term algorithm can cover all procedures that provide a standardized set of steps solving a specific, repeatedly encountered problem. In this sense, any recipe in a cookbook is an algorithm, allowing for the standardized, step-by-step approach to solving a specific problem, such as preparing a given dish. Algorithms in this sense lay at the heart of many standardized practices of modern life, be it cooking, sports, or the pursuit of hobbies. They are an essential part of teaching trades, skills, and professions, and they are a crucial feature of organizations guaranteeing their proper and standardized workings. Examples include internal administrative guidelines within government bureaucracies, police departments, or large companies for addressing specific, repeatedly encountered tasks. Algorithms, in this sense, are a core feature of modernity, standardization, and professionalism. Currently, we tend to associate the term algorithm most prominently with regard to computers and the automation of processes or decision-making. Fundamentally, when used in the context of computing, the term algorithm means the same as in other areas, but the series of steps to solve a task must be computable by a machine. Let's try a hand at a definition. Here I quote Knuth. The modern meaning for algorithm is quite similar to that of recipe, process, method, technique, procedure, routine, rigmarole, except that the word algorithm connotes something just a little different. Besides merely being a finite set of rules that gives a sequence of operations for solving a specific type of problem, an algorithm has 5 important features. End quote. For Knuth, these features are finiteness, definiteness, input, output, and effectiveness. Let's get back to our argument. According to this definition, an algorithm must be finite. In other words, it must complete after a series of steps. These steps need to be clearly and unambiguously specified. They need to be definite. An algorithm works on inputs and returns outputs. Those stand in a specified relation to the inputs. Finally, following Knuth, algorithms should be effective in that each of the steps specified to solve a task should in principle be doable by a person using pen and paper. These sets of features can be used in the analysis of algorithms to compare the performance of algorithms in translating inputs into outputs. An important element here is the number of steps necessary to perform the task, with a smaller number of steps being more efficient and demanding for less computing time. Algorithms lie at the heart of computation. They are the basis for any computational operation, and the discussion can rightly focus on the math, expression in code, and efficiency. But algorithms are increasingly used to solve tasks that are not predominantly restricted to technical contexts, but also have social consequences. Algorithms shape digital systems that directly impact or even interact with people. Accordingly, in their analysis, we have to move beyond merely technical questions to social, psychological, and structural questions. For this, we have to turn to the fields algorithms are used in, tasks they are set to solve, direct effects on people, and their indirect effects on the societal fields and social contexts they are deployed in. Computational algorithms are the key in translating data into action and insight. In the episodes on data, we saw how data makes the world readable, offers insights about regular and potentially causal connections between entities, and allow for actors to plan and adapt for the future. Algorithms can build on these potentials and realize them. In fact, given the massive scale of newly available data, the automation of analysis and action through algorithms becomes a condition to do so. It is no surprise, then, to find computational algorithms to be used in a wide variety of contexts in which they shape and impact social and individual life. This variety is too broad to cover it here comprehensively. However, we can categorize their uses in 3 categories that illustrate different goals, workings, and concerns. These are the use of algorithms for insights, decision support, and action. Let's start with a discussion of the use of algorithms for gaining insight. Algorithms are widely used to provide insight. Data do not speak for themselves. Data-enabled insight depends on analysis. This is done with algorithms designed to process and analyze data to uncover patterns, trends, and hidden relationships. Examples include data visualization tools, data mining techniques, and certain machine learning models used in exploratory data analysis. Algorithms like these are essential in sectors like research, business intelligence, and academic studies, where raw data must be transformed into meaningful insight. While there are many different kinds of algorithms for data analysis, it is helpful to differentiate between 2 approaches. Many algorithms transfer mathematical calculation procedures into computer-readable routines. Programmers provide computers with a predefined series of steps of resolving tasks in data analysis. This allows computers to automatically perform data analysis on vast sets of data and providing insights. This includes data preprocessing, sorting, searching, clustering, and pattern recognition. Since all steps and analytical procedures are predefined, these approaches are reliable and comparatively easy to explain, but depend on the quality of the predefined steps and rules. Let's have a look at an example. Let's assume a political campaign has a dataset with information about people. It is interested in gaining insight into which individuals in said dataset are likely donors. One easy algorithm that allows this is the k-nearest neighbors, KNN. Roughly speaking, KNN does the following. The campaign has a dataset with information about people, such as their age, income, the number of times they have voted in the past, and whether they have recently donated. Now, for each new person entered into the campaign database, KNN calculates whether they are likely to do so in the future by looking at a small set of people in the dataset, let's say 3, that resemble them with regard to characteristics that the campaign has information about. In our case, this would be age, income, and the times they have donated in the past. If most of these similar people have donated, there's a likelihood that the person of interest will be open to donate in the future. If not, not. Let's get back to our argument. Alternatively, one could use also machine learning algorithms. Machine learning algorithms also operate based on a set of predefined steps, but many introduce stochastic and probabilistic elements during their execution. This incorporation of randomness means they may not always yield identical outputs when executed multiple times with the same input, making them less deterministic in nature. Machine learning algorithms tend to be more data-intensive than other approaches, but also are more responsive to unforeseen patterns in data and temporal shifts. On the other hand, due to the stochastic and probabilistic elements, they can be hard to interpret and their returns difficult to explain or assess, leaving some uncertainty with regard to their use in real-world scenarios. Let's stay with our previous example, but now look at how it could be solved through a machine learning algorithm. Let's say a random forest algorithm. The campaign begins by collecting a comprehensive dataset on past donor behavior. After ensuring that the data is cleaned and processed, relevant features are selected and processed appropriately. The campaign randomly divides the dataset into a training set, let's say 80% of the records, and a test set, let's say 20% of the records. Using the training set, a random forest model is trained to recognize patterns and characteristics that are indicative of donation behavior. The model's feature importance ranking is analyzed to understand which donor characteristics are more predictive of donation behavior. The trained model's performance is evaluated on the test dataset using appropriate metrics to ensure it predicts accurately and generalizes well to unseen data. Once satisfied with the model's performance, the campaign can use it to predict the likelihood of new potential donors making donations based on their characteristics. Let's return to our argument. Both traditional and machine learning algorithms offer valuable insights, yet they possess distinct strengths and limitations. Traditional algorithms are particularly helpful for datasets with a limited number of features per observation or low dimensionality. In such scenarios, the design and application of classical statistical models are straightforward, and the simplicity of these algorithms often suffices. The limited variables mean there's minimal benefit from the complexity of machine learning algorithms. On the other hand, for high-dimensional datasets with numerous features per observation, traditional algorithms quickly reach their capacity. It's in these complex scenarios that machine learning algorithms shine, leveraging their ability to handle vast amounts of data. However, these algorithms are resource-intensive to train. Their often stochastic and probabilistic nature can make them challenging to interpret, leading to potential skepticism and criticism from the public. For tasks requiring high reliability and transparency, the complexities and opacities of some machine learning models may be less suitable. Actors in various fields rely on algorithms to provide them with insight. Examples include campaigning, in which parties use data and algorithms to identify likely voters, contributors, and model likely voting behavior. Another example is the use of usage data by newsrooms to identify trending topics and features of successful stories. In these and other cases, the use of algorithms to generate insight not only changes the behavior and opportunities of people using algorithms, it can also lead to a reconfiguration of structures, organizations, and institutions in the field around new opportunities and demands associated with their realization. This becomes clearer once we look at an example. Famously, the US presidential campaigns by Barack Obama in 2008 and 2012 relied heavily on algorithms to generate data-enabled insight about voters, donors, and volunteers. These insights were so important to the campaign that it changed the traditional organizational structure of political campaigns and put digital and analysis specialists at the core of the decision-making group. Key to these adjustments has been the power of data and algorithm-enabled practices for campaigns to generate insight about potential donors and to provide ways of maximizing their contributions to the campaign. These successes generated a whole industry of donor analytics and became crucial to campaign practices within the Democratic Party across the ticket. But heavy reliance on donation requests in campaign communications with their supporters might over time have contributed to a shift in the relationship between party and supporter. Mika Sifry argues that this practice has led to a largely transactional and commodified relationship between the party and its supporters, severely reducing the resonance of its progressive claims and over time contributing to a donation fatigue. This is an example that, over the course of few campaign cycles, innovative early users of algorithms provided insights and a competitive advantage for early adopters. The public perception of the contribution of algorithmically gained insight to electoral success created a large set of imitators who adapted the same techniques and approaches. This then led to adaptation and changes in the behavior of people, rendering formerly successful practices mute. If we want to understand the use and impact of algorithms, we therefore must turn beyond the narrow analysis of the workings of algorithms and their uses and take a broader look at societal fields and action and adaptation over time. Let's get back to our argument. Of course, just because an algorithm does provide a result, that doesn't make it true or useful. In the interpretation of results provided by algorithms, people need to remain aware of potential limitations and sources of errors. This includes translating the general limitations of quantification introduced in the episodes on data to the specific contexts algorithms are used in. More specifically, it also includes critically interrogating whether the steps in the analysis reflect both the characteristics of the underlying data and the problem they are supposed to solve. But let's take a break for now. In the next episode, we will focus on algorithmic support for experts and laypeople in everyday life. As always, the script to this episode can be found online on the course website, https://digitalmedia.andreasjungherr.de. There, you will find detailed sources, references to further reading, links, and preparatory questions for the exam. This was Tech and Politics, a podcast by the Chair for Political Science, especially Digital Transformation, at the University of Bamberg. I'm Andreas Jungherr. Have fun reading, and see you soon.